Yeah, so I welcome you all for the fifth talk of the series, Mechanics of Materials Talks. And today we have pleasure to have Professor Sergio from TUDelft. And yeah, I don't have to introduce, but I just read few things about him for a better introduction. So he's associate professor in aerospace structure and computational mechanics group at TUDelft, Netherlands. And he also worked as assistant professor at University of Pennsylvania. And he also did postdoc at University of Michigan. And he did his PhD from Caltech and MSc from University of Houston. And his research area are basically multiscale modeling and simulation of advanced structural materials, such as high-strength multi-phase steel assisted by transformation-induced plasticity, and lifetime modeling of self-healing, high-temperature thermal barrier coating systems, and topology optimization of functionally graded materials and composite materials. So, yeah, over to you, Sergio.
All right. Thank you, Prabhat, and thank you, Sumit, for this very kind invitation. It's a real pleasure to have the opportunity to talk to all of you. And I'm going to be talking today about a topic that has been a bit of a hobby for me over the last couple of years. And it does combine two important things, which is fracture mechanics on the one side and then multiscale modeling on the other side. And what I'm going to present today is actually not just my work, but it's a work that I have been doing in collaboration with students. And I've been very fortunate to collaborate with Niels van Hoorn, Wim Westbroek, Christian Hirsch, Gijs Jong, and Ruben Suarez Millan. All very smart people. So I decided to have a little bit of a roadmap.
Sorry to interrupt you, Sergio. Just I forgot to tell audience that you can type your questions in Q&A, and I'll read out to Sergio, and we will discuss those at the end of the talk, and we will also go live interaction after the end of the talk. Yeah, sorry. Yeah, sorry, Sergio.
No problem. No problem. So I decided to put together a little bit of a roadmap for today's presentation, and one is why do we need to, or why is it interesting to use multiscale methods for fracturing composite materials? And then after that, I will switch to a topic that has perhaps not had too much attention. Some people have worked with this, which is why is it fracture, a multiscale fracture, different than what I will call the classical multiscale? And so I will talk about the differences between volume averages and surface averages. And that is going to lead me to a few new concepts in terms of how do we define the macroscopic quantities, the so-called effective quantities, when we do the scale transition from the small scale to the large scale. And related to what people normally use in multiscale analysis, which is a representative volume element, I will argue that we have to work, when it comes to fracture, that we have to work with the notion of a representative surface element. And time permitting, and hopefully I will talk fast enough to finish all the slides. Time permitting, I will then show you an application of this methodology, which is why is it interesting to use multiscale, and among other things in terms of studying effects of defects at the microscale. And so how those defects affect the macroscopic behavior. So with this roadmap, let me get started then with the first topic, which is why multiscale fracturing composites. And to motivate this, usually all the multiscale talks always have a multiscale picture, and this is no different. So let me start with the macro one. Because I work in aerospace structures, I have to start with an aerospace structure. So typically you would have here a, in this case, is a macroscopic structure, which is a rocket, one of the Arianes. And then nowadays, a lot of these components are made out of, structural components are made out of composite materials. Yeah? So when you start to look at the different parts that are in the rocket, then you would find some composite. And as many of you may know, the composite is typically a laminate. And in the laminate, as you zoom in even further, you would find then individual fibers which are oriented in different directions at the level of the ply. And so the multiscale in this case refers to particularly, in principle is general, so it could be applied to any kind of composite material, but I've decided to concentrate mostly on typical composites which are used in aerospace. In that case, when it comes to this type of materials, it's important to remember how they break. And the reason for that is because this talk is going to be mostly on the fracture aspect. When you look at the ply level or sub-ply level, the mechanisms are usually this one. So either you could have the fibers that may be breaking. In this case, this is an example of some transverse cracks, and then transverse cracks implies cracking of the matrix. But also the fibers, individual fibers can separate from the matrix, as you can see here. So there is debonding between the fibers and the matrix interface. Or you could have also delamination, which is when two of these plies separate. In any case, what is interesting in terms of why do we want to analyze this is that when we develop a new composite material, we would like to find the relation between the individual components and the performance of the laminate. Yeah? So for issues of material development, we would like to find out what is the relation between the sub-ply constituents and the performance of a laminate. So how do we do that, and what is important in this context? Well, first of all, we have to understand in terms of the different length scales is that when we talk about the strength, the fracture strength, or the fracture energy, when we talk about that property at a given length scale, it is connected to the constituents at the lower length scale, which may have then different properties. And so the strength and the fracture energy at the lower length scale is different than the one at the larger length scale. And what it depends then, the effective properties will depend then in terms of the constituents, but also in terms of how they are laid out. Yeah, so in terms of different plies, orientation. So it has to do with the microstructural details. It also has to do with the fact that perhaps we also have defects. And that in some other cases, we may have an interaction between other inelastic behaviors, such as plasticity, that then connects with fracture. For this talk, I'm not going to include other inelastic behavior, so that's still in the to-do list. But it is also a very important effect that you carry on from one length scale to the other. When it comes to trying to decide what is the best way to try to characterize this material. So people have looked at many different ways of modeling fracture. So the traditional fracture criteria that is used for composites, you try to incorporate then the properties of the matrix, the properties of the interface. In this case, the interface refers to the bonding between the fibers and the matrix, and the fibers themselves. So if you look at the whole spectrum of criteria that is used, fracture criteria that is used in aerospace for composite materials, the first thing that comes to that is remarkable is how we try to combine that information, but it's always done in a rather phenomenological way or semi-phenomenological way. And what that implies is that we need to have extensive experimental calibration to find out what are the parameters that have to go into these models, which is fine in principle. I mean, it's expensive, but it's something that needs to be done. But one thing that happens is that one of the limitations of the current approach is that often this type of criteria is limited to damage initiation. So it does not tell you something about how a crack is going to propagate. It only tells you when the crack is going to initiate. You could argue that for design purposes, it's only sufficient to know when it's going to initiate. But in reality, we want to have a design in which we also take into account the propagation part. So in order to tackle these problems or limitations, I would say, for the traditional failure criteria, which is, it is perhaps too phenomenological. It requires a lot of experimental calibration, and in particular, that is limited to damage initiation. One of the possible ways to move forward is to look at multiscale methods. slightly less phenomenological approach, as I like to call it. Now, when it comes to fracture mechanics, you may know that there are many different methods to choose from, and everyone is very passionate about a different method in terms of fracture mechanics should be done this way or that way. I have to make a choice, and what is quite common in terms of numerical modeling these days is to use a cohesive zone modeling. And just for the purpose of this talk, I would like to refresh your memory in terms of what is a cohesive zone model. I mean, for those of you who know it, just bear with me. It will not take long. Cohesive zone model is essentially in itself is phenomenological in the sense that what we do is that we look at a crack, and then there's a crack front in here, and there is a process zone, or the so-called cohesive zone in here, where the fracture process is occurring. And what we do is that we model that with a cohesive relation inside this cohesive zone. So if we zoom in terms of the process zone, we will have essentially the crack itself is here, and then the crack surface or the crack tip, if you want, in 2D. It is modeled through this cohesive zone with a cohesive relation. And a cohesive relation would essentially tell you that the material in front, it hasn't damaged yet, so it can transmit any load. Once you reach the fracture strength of the material, at this point, then the material will start to degrade in terms of its capacity of transmitting load. And so as the crack opening or the effective crack opening increases, then the capacity to transmit the load decreases up to a point where it goes to zero, and then effectively you have a crack. So the two surfaces have completely separated. And the two important parameters here are the fracture strength and then the fracture energy, which is the work dissipated in the process of creating this crack. How do we connect this to multiscale modeling? Well, so this would be the modeling that I'm going to use for the fracture part. And then the other choices in terms of what type of multiscale modeling are we going to use. A rather popular one is the so-called FE square approach. And so what that stands is that you have to solve two finite element problems. So one at the so-called macro scale and another one at the micro scale. In the sense that if you have a crack, as indicated here, and you zoom in into a given point, then you may see a microstructural volume element where the fracture process is occurring in more detail. And then somehow you have to average this and then pass the information to the microscopic crack. This is one possible approach, but it does have a little bit of a limitation in terms of the computational power that is required to solve the problems on the fly. And we can, in fact, bypass this by looking at an alternative approach, which is what I'm going to do. And that alternative approach is to establish a priori a macroscopic cohesive relation, an effective one. So we start as input, we give the microscopic cohesive relations for each one of the constituents, plus we give the information about the distribution of the faces. And then by solving a series of boundary value problems, we can then extract the information through post-processing. So the idea is that you solve, when it comes to solving a macroscopic problem, instead of having to always go back to the microstructure, you said, well, I'm going to solve this once and for all at the microscopic level, establish an effective cohesive relation, and then I would use that as a single scale approach. So in a sense, it is a single scale approach that incorporates through the constitutive relation, through the cohesive relation, the microscopic information. Now that approach has certain advantages, which is that immediately, if you look at trying to introduce the information in the modeling, we can pick, for example, we have a matrix, an interface, and fibers, and we could do a simulation whereby we, from the outset, we put the information in terms of the cohesive relations for each one of the constituents. So in particular, if I were to do a numerical simulation, and I have here a finite element mesh, where I have a fiber, and I have matrix, and I have an interface, we could use, this is a very traditional modeling technique, so it's just so-called cohesive elements, whereby at the edges of the bulk elements you insert a cohesive element. And depending on where those cohesive elements are, you can indicate that is a cohesive element for the fiber, or the matrix, or the interface. So this is considered to be the input for the simulation. Now the output, and that's the question, is what would be the effective cohesive relation for the composite? So that's the question. And the idea is that the multiscale method should allow us to obtain that macroscopic cohesive relation. And it will tell us what the strength of the composite is and what the fracture energy of the composite is. So how do we do that? And what is the advantage of that? If we do it this way, then I would claim that an advantage is that we can immediately, without having to think too much about it, we can incorporate the information about fracture energy of each one of the constituents, because you do it in a one-to-one fashion. Secondly, you don't necessarily have to think too much in terms of indicating what the fracture mechanism is going to be, or what the effective properties are going to be, because in principle, this should come out as an output of the multiscale simulation. One extremely important, and I emphasize this because we discovered that it is quite important to be very careful with this. One important requirement is that as we connect the information from the lower scales to the larger scales, we really have to make sure that they are energetically consistent. So I will put it in red letters here. So it's a critical requirement. We really have to make sure of this. So for example, if we go from the supply to the laminate level, we have to make sure that these two descriptions are consistent from the point of view of energy. And that brings me to the next point of this presentation, which is multiscale fracture. And I would claim that here the difference is that we have surface versus volume. To make my points, let me go back to a sketch that I had before, and then we're going to look at a laminate. And I'm bringing it here, couple of names that might be familiar to anyone who's done multiscale, so Hill and Mendel, and the so-called Hill-Mendel condition, which is what I just mentioned, the condition of being energetically consistent. And this one I call the volume-based Hill-Mendel condition, which is the traditional one. In that case, if we look specifically at a region here in one of the plies, inside one of the plies, perhaps it might be a little bit too small on your screen, but I will indicate what it is by making it a little bit bigger now. So if we zoom in here, we have a given region, and then in this region, we may have a crack, and this is a very detailed description of a crack. And we have a so-called microscale, or microscopic rather, volume element. So this microscopic volume element that we have here, inside we may have a crack. And that crack is called here gamma, and the border of this domain is called del omega. And this would be the microscale description of the crack. Now, when we look at a microscopic state here, we are actually not going to use all the details of the microscopic description. We're simply going to use an effective or an equivalent microscale crack. And for that, we have to think in terms of an effective traction and an effective crack opening, and also an effective orientation, because here you can see that this is a path that changes orientation, but somehow all of this has to become just one orientation at the microscale. Here on the top, you see that I've written the expression for those so-called micro powers. So taking the traction on the boundary, multiplying it by the displacement rate. So the dot here is the time rate of change of the displacement. And that gives me essentially the power that is exerted on the external boundary of this microscopic volume element. The condition for the connection rather with the macro scale is that I now look at this as given a point. It's a macroscopic point. And as such, as we do in continuum mechanics, there would be a stress tensor associated to this point, and there would be a strain rate. And those are the quantities indicated here on top. So sigma m is the macroscopic stress, and this epsilon bar dot is the microscopic strain rate. Now, if I want these two descriptions to have to be connected, to be related to each other, then we have to make sure that they are energetically consistent. And what that means is that if I compute the power this way, or I compute the power this other way, they have to be equal. That's the notion of consistency. These two quantities have to be equal. This is the so-called Hill-Mandel condition. And locally, it's relatively simple and straightforward to make sure that it's satisfied. The only thing, one possible way to do it, is not the only way, but it's one very popular way of doing it, is just to use periodic boundary conditions. So PBC here stands for periodic boundary conditions. So you get satisfied this a priori if you impose periodic boundary conditions. And even if you have a crack, that doesn't matter, it's still satisfied. So we're good. We're good in the sense that these two descriptions are consistent with each other. And the way to look at that is that if you apply essentially the divergence theorem, you could show that the micropower, which is this quantity here, is equal to the volume average of the stress times the strain rate. So comparing this quantity to that one, you see, okay, but these two are the same. So to make sure that this is satisfied, I just need to define the macroscopic stress as the volume average, and then everything works. And that's exactly what happens. So to make sure that the Hill-Mandel condition, volume-based Hill-Mandel condition is satisfied, then we just simply say the macroscopic stress is defined. So the symbol that I'm using here is essentially a definition. So I define the microscopic stress, the effective stress, as being the volume average. And this is something that is very commonly done in multiscale methods. You don't even think about it, just simply say, what is the most natural way to define the macroscopic stress? Well, take the average of the microscopic one, and that's it. That's what it should be. And so we're all happy. But there is a little bit of a problem when it comes to fracture. When it comes to fracture, there is localization, and typically it occurs in a very narrow region, which in the limit, it becomes a surface. And then that creates two issues. The first one is from the point of view of convergence for multiscale. Usually when you look at convergence in multiscale, you have to define, or you have to identify, the so-called representative volume element. And to do that, you start with microscopic volume elements. You make those bigger until the effective properties do not change anymore. So the convergence here is exactly the opposite of what you would do with a mesh refinement. Here you have to make it always bigger. And once it is big enough, and then the effective properties are the same, they do not change anymore, then you have a representative volume element. The problem here is that as we make the volume element bigger and bigger, the ratio between the crack and the volume, so this is surface to volume. Well, this is 2D, but you have to imagine it's 3D, so it's per unit depth. But the relation between surface to volume is not constant. So the bigger I make this, then immediately I do not have convergence. And this is something that colleagues have identified long ago. So they decided, okay, well, we cannot work with these volume averages because they don't converge and they don't give us a representative volume element. But if we just focus on the region where it localizes and we take an average there, then it would work. And that is indeed the case. And what we have done lately is to formalize this much more than what it was done before. The other thing that is important to mention is that and another motivation for having to have this surface averages instead of volume averages is that as it refers to the fracture process, then it turns out that one has to separate what happens in the bulk material, which is far away from or away from the crack, and what happens at the crack surface itself. So that's another important thing, that the effective properties for fracture, it is going to require us to separate the response of the crack in terms of this is a crack and the surrounding material is really part of the bulk response. How do we translate that into another type of Hill-Mandel condition? So it's no longer a volume-based Hill-Mandel condition, but a surface-based Hill-Mandel condition. It's essentially something very similar in the sense that you have to look at what is the power that is occurring through the fracture process. So we look along the crack and we look at the tractions and we look at the local crack opening rates. You compute the power there. That integral is done along the crack itself. And this is essentially how you integrate and you get the total power expended by opening the crack. And so the symbol here indicates this is a surface-based integral. And somehow this has to be equivalent to a macroscopic crack. So the macroscopic crack only has one effective traction, one effective crack opening rate, and one effective orientation M, and also one effective length. And so these have to be energetically equivalent. So these two quantities have to match. And that is a surface-based Hill-Mandel condition. There are two issues that occur here again. One is that if we satisfy the volume-based Hill-Mandel condition, that does not imply a satisfaction of this surface-based Hill-Mandel condition for fracture. So that was what motivated part of this work, that all of a sudden I realized something is not working here. And the other thing that doesn't work, as you may expect, is that if we want to impose consistency, if we would like to impose consistency, and if we need to look at what is, in fact, the effective traction and the effective crack opening rate that we need to use. The problem is that if we satisfy or we define the effective traction as a surface average and the crack opening rate as a surface average, those two simultaneously, we will never have this quantity match. Maybe in some cases approximate, but in general, they don't match. And one way to look at that is to see exactly what the volume-based Hill-Mandel condition is telling us. There's a certain quantity here, which is called a fracture strain. It's given more detail in other papers. But what is important is this result here. This is the power that is associated to the process of fracture. And here you have a traction-like quantity, which is in fact different than this T here. And so this is, in fact, the quantity that we have to look at. And this motivates two different ways to look at candidates for effective traction. So what we did was to look at the two most obvious ways to define a traction for fracture. The first one, perhaps the most obvious one, was to say, well, I could take the traction along the crack and take an average of that. It's a surface integral of the traction and define an effective traction as being the crack average traction. The other possibility is to say, well, to get a traction, I need two things. I need a stress tensor and I need a normal. And then I could take the average normal. This is the average orientation of the crack. And then this vector, I could take the average stress, but this one is on the not only on the crack, but also on the surrounding material. I could take the volume average and then this tensor acting on this orientation, and that gives me another definition of a traction. So we have these two distinct definitions of tractions. By doing so, we could then think in terms of one of those two perhaps is the right way to think about the traction. As I said on the previous slide, the problem is that if we define the crack opening as the average, and I combine that with this definition, which is an average, I will not satisfy the surface-based Hill-Mandel condition. So following a pragmatic engineering approach is to say, well, it has to be either one of the two quantities. We don't know which one. So let's try both, and let's try a linear combination. So I propose a effective traction as being simply a linear combination between the crack average one and the one that is based on the volume average. It's just a linear combination. So if it's alpha is equal to 1, it's this one. So if alpha is equal to 0, then it's the other one. And then to see what happens. And so the idea would be to have an adjustable parameter here, alpha, to satisfy the Hill-Mandel condition. And there is a formula for that. We said the best match is given by this expression. The details are not that important. You could find that in some of these references. But I would rather show you the results to see what in practice it looks like. To do that, we have to do some simulations. The simulations, I'll skip a little bit of the details, but I'll just tell you it's rather straightforward in the sense that you take a sample, you create a geometry from there, you put a mesh, then apply some periodic boundary conditions in this case. Then we have to insert cohesive elements everywhere, and then we specify what is the matrix, what is the fiber, what is the interface, and then we run the simulation until we load this in a way until it cracks completely. And then the key aspect of all this is to do the post-processing. So this is where things are interesting. I got a few questions in the last couple of years from my colleagues in terms of is it allowed to use periodic boundary conditions when you have a crack? That was a matter of discussion at some point, and my claim is that it is. And I will illustrate this very quickly. So what it means is that it's just important to understand how to interpret it. To illustrate this is that suppose that you have this domain here, and this is periodic, both in horizontal and vertical direction. So it's a pattern that repeats itself. And when it cracks, the same thing happens. That is to say that if this is just a computational domain, this square here, it doesn't need to be a square, but let's say a rectangular domain, and it is periodic in both horizontal and vertical directions, then if a crack exits here, then it has to reappear here. And if it exits here, then it has to reappear here. So by following periodicity, then if you see this domain here in white is where the cracks are, well, you have to repeat those. And then you get this crack here, but then you also get this crack here. And if you look carefully, you have a crack here and a crack here. So you have all these parallel cracks. And that was an argument that was used in the past to say, well, then it means that this procedure fails because it makes no sense. However, we sat down and then we looked at this in more detail. And what we discovered is that if you do a shift of this domain, yeah, so let's say that this is the original domain, but now you shift this thing all the here. You then have a single crack. All the other parallel cracks have no influence on the computation. So in a sense, it's just a matter of interpretation. As you can see here, I've shifted this here. And we have shown this in this publication here, that the average strain in the original domain is equal to this average strain in the shifted domain. And so essentially, the parallel cracks can be safely ignored. They have no influence on the results. And so that's the claim that we can use periodic boundary conditions. We still get the proper results. It's just a matter of interpretation. And the other point is that whether that would limit the orientation of the crack, and my claim would be that in principle, no. You could have orientations which are rather arbitrary, and the shifts doesn't need to be just to move the square. You could split this into very complex shapes and reassemble them, and then you would get cracks of any kind of orientation. Now with this, let me show you what happens in one of the simulations. So this is a typical simulation where we have some of the cracks, and I've plotted here two curves. One is a solid line, and this is the externally applied work that we apply here on this domain. Yeah. The other quantity here is the product between the average stress and the average strain rate as a tensor. And if the Hill-Mandel condition works, then these two curves should coincide. And then we basically computed those two separately, and it's a very good match. And the reason why this works is because we are using periodic boundary conditions. So the volume-based Hill-Mandel condition works very well. Now, when it comes to the crack itself, so we identify where the crack is, and we do that by having an algorithm that allows us to extract the location of the crack. We could take integrals there, and we can compute quantities which are related to the crack only. The solid line that you see here in blue is in fact the actual energy dissipated through the crack process. The two other lines are related to the two definitions of two alternative definitions, if you want, of the traction, the effective traction. This one here is the dash or the dots here. This one corresponds to a definition of the traction based on the average. And so you see that is here below. If we use the volume-based definition, which is the dash line here, this is the volume-based definition with the volume average of the stress, we get this curve here on the top. So the difference between the top one and the actual one is because this one is actually taking into account effects that happen in the surrounding material, which are not directly related to the fracture process. And is, interestingly enough, the one that is just based on the average of the traction on the crack underestimates the amount of energy dissipated. However, if we do a linear combination between these two, and I'll show you what the result is for this parameter alpha equals to 0.4, we have a relatively good match. It's not perfect. It is approximate, but it's relatively good. It's much better than the two other ones. So that justifies the effect of using, or the reason for using this adjustable parameter here, alpha, then to try to get the proper effective quantities for the crack, such that it is energetically consistent from the point of view of fracture. And when it comes to the effective traction separation loss, you could argue that the effect is not that big in this case, but it is still not noticeable. This would be the effective traction separation law. If we use the crack average, this one on top would be the effective traction separation law if we use the volume average of the stress, and this one in the middle is the one that we obtain if we actually use this upper bound and this lower bound with a parameter alpha equals to 0.4 in this case. So we were quite happy to have a method to approximately satisfy the Hillman-Nell condition. And we published a paper and we thought, okay, we're done with this. But then doing some more analysis, we discovered later on an issue. And so let me switch back to this thing where we found an issue, which is that if we look at the this method, it worked very well whenever we had this small contrast in the fracture properties. So the simulations that we did were mostly matrix cracking and the bonding between the fibers and the matrix. And the difference between those fracture energies was not that big. When we move to another setup where we actually had fibers running in this direction and fibers running in this other direction, so a 0-90 laminate if you want, things started to look different. Here we had a new mechanism, which is that we also had fiber breaking. And here the strength that we're talking about is much larger than the one in the both the debonding and the matrix. And so when the contrast between these fracture properties was very large, we started to notice some discrepancies. And so that pretty much forced us to start to rethink this. And so we went back to the boarding let's say we went back to think in terms of how do we solve this issue. And so we started to think again, and we thought about new scale transitions methodologies. So I will introduce those, and I noticed that I have to really hurry up a little bit because I still have quite a bit of slides. But we started to look at different scale transition methodologies. So the first one is the same one that I showed you before. So it's this with this adjustable parameter alpha, which gives us an approximation of the Hillman-Nell condition. What we thought is that, okay, we need to make sure that it's consistent from the energy point of view, and we adjusted this with this parameter alpha. But then we went back and they thought, why don't we just make sure that it's exactly satisfied? Not just approximate, but exactly satisfied. So what do we need to do? So we knew that something had to give up. So we cannot have at the same time volume surface averages and the Hillman condition satisfied at the same time. So we had to adjust something, and then we had to give up on a sacred quantity, which is the average quantity. So we came up with two very simple approaches. So one is what we call this kinematic space approach, where we make sure that the Hillman condition, the surface-based Hillman condition, is exactly satisfied. And we do so by redefining what the traction is. So we compute the crack opening as the average, and the effective traction is whatever is required to satisfy the Hillman condition. So in fact, we use Hillman condition to define the effective traction. And you could play this game in a different way. You could say, well, we could do it the other way around. So why don't we define the effective traction as an average? And now we give up on the crack opening. So we say the crack opening is no longer an average. It is whatever is required to satisfy the Hillman condition. So to give you an overview of the methods and a bit of the formulas, let me start with this kinematic base method. So the kinematic space method, we define here the effective crack opening rate as the average, and we propose as a definition of the traction. It's no longer an average, but it's a modified average. And this is what bad students do in the following sense. It says, well, this is the solution that I would like to have. And this is what I get. And if I simply multiply by this factor, so it's essentially saying I have a wrong solution, but I can get the right solution by essentially multiplying the quantity that I have by the right solution, and I divide it by the wrong solution. That's exactly how this works. So we know what we want to get at the end. So we modify the traction, this average, by this quantity such that we satisfied that the average of the product is equal to the product of the averages, or rather the average of the product is equal to the product of the effective quantities, which is what we want. Similarly, this kinetic space method is the other way around. So we define the traction as the average, and we modify the crack opening rate in a way in which we satisfy the Hillman condition. So with that, we have three methods. And I would also emphasize that this is not for computing the quantities. This is for post-processing. So we take the same data of the simulation, and we do three distinct ways of doing the post-processing. So three distinct ways of defining what are the macroscopic quantities. In one case, the Hillman condition is satisfied approximately. In the two other cases, satisfied exactly. For these two methods, the crack opening is the average. In this last method, it is not. In this method, it is not exactly the average, it's approximate. It could be exact if alpha is equal to 1. In this kinematic space method, it is not the average because it is just adjusted to get the Hillman condition. So you cannot get those three things at once. That's the problem. So you have to take two, and then the other one is an approximation. With that, we started to run some simulations, but now with fibers also running in this direction to make it a little bit more interesting. And if you look at the fracture properties here, I mean, this is huge compared to the in plane, right? So the fracture strength here, we're talking about 5 gigapascals. Whereas for the matrix, it's much lower. This is about 80 megapascals. So it's quite a bit of a difference between what the matrix can carry and what the fibers can carry in terms of the strength. So we started to look at this fracture process, and then here we had one example in which we started to pull. So this is uniaxial extension on the 090 specimen. So you have fibers running towards you, and then fibers running on the horizontal direction. And we start to pull, and we look at the fracture process. And we started to also plot the different quantities of interest for the process of fracture and deformation. So here at the bottom, you have some time axis, and then here is the power. And the different quantities indicated here. The line here in black is what you would obtain if you don't separate the crack from the surrounding material, which a lot of people actually do. They just say, well, this is my effective relation. I just do a volume average, and this is what I get. But you have not separated the bulk from the crack itself. If you separate the bulk here from the crack, you get a different story. In fact, you could see that there is an enormous amount of dissipation here on the crack itself, and the surrounding material, actually, you're storing elastic energy. So that's why it's important to separate the two things. I mean, as you pull and you're deforming the bulk material elastically, and the inelastic process is actually occurring at the crack itself. And so we dissect, in a sense, what is the purely fracture process from the elastic deformation in the surrounding material. So the line here in blue is what we should match for the crack. And we applied the two different methods that I just mentioned in the previous slide. So one is a kinematic space, the other one is a kinetic space. And in both cases, we match exactly this Hill-Mendel condition. So our effective properties are such that we will reproduce exactly the curve that we want to have. It is consistent from the point of view of energy. What is interesting is that it gives you very different effective traction separation laws, the post-processing part. And to show you that, this is the previous method that I mentioned with an alpha parameter for this type of deformation. So you get this traction separation. Here you have the effective crack opening, and here you have the effective traction for the process. And as you can see, the values around here are what you would expect from looking at the volume occupied by the fibers divided by the volume occupied by this section here. Yeah, so you don't get 5 gigapascals, but you get, in fact, a scale version of that, because you don't just have fibers all over the place. You do have matrix in between. If you now look at the other method, which is this kinematic space method, you see here that it's picking up the, as you can see, as deformation occurs around here, there's quite a bit of fracture in the matrix first. Yeah, so first the matrix cracks at a relatively low stress because the matrix cannot carry too much load, but the rest is being carried by the fibers. And so at some point, first you have the matrix cracking, then it stops, and then you load the fibers, and then the fibers start to break. Now, what is happening here is that there is this rather strange behavior here. It goes to a rather large peak here. And we'll come back to that after I give you a little bit more information. The other point to notice is that these two curves have to end up at the same point, because these two methods use exactly the same average for the effective crack opening. If I now do a simulation, or the same simulation, but I post-process the data using the so-called kinetic space method, we get a different curve. So this one here in red, it actually looks like the approximate Hill-Mendel condition method before, but it doesn't end up at the same point. It gives you it predicts a larger effective crack opening. And that is because this crack opening is not computed from the average, but rather it says the average is whatever is required for satisfying the Hill-Mendel condition. And so it actually gives you the proper estimate in terms of the energies. The approximate Hill-Mendel underestimates the amount of energy dissipated. That is more accurately estimated by the crack opening. I will come back to this in a second in a slide that comes soon. We tried this also with another case. So we did here with a shear and a biaxial extension. And this one, as you can see, the matrix cracking is much more significant. So before the fibers break, there's a very significant deformation due to matrix cracking. And that is observed here in the post-processing as well. So here, first, initially, you have matrix cracking. It is quite significant, but it dissipates very little energy. So even though it's a big crack. It has occurred at such a low stress that actually the energy required to break the matrix is not that much in comparison. Most of the power expended is by breaking the fibers, which occurs around here. So it starts to already occur around here, but you see that breaking the matrix is not that difficult, and then it's mostly breaking the fibers that consumes most of the energy. And so again, we try the two methods for average, and we match exactly this curve. So we are very consistent from the point of view of energy. And again, we get very different traction separation laws in terms of the effective response. I will show you that in the next slide. This is the first method, which is an approximate Hill-Mandel condition. You observe here the effect of the matrix cracking already. And then at some point it decays. The other method is the one where we average. The effective crack opening is the average of what happens in the matrix. And then, as you can see at this about 80 megapascals is where there's the onset of matrix cracking. And so there's a huge opening that occurs here, as you can see. But at this point is where we do the post-processing for the fibers breaking. And to compensate, because we have moved so far out in terms of the crack opening, it overpredicts the tractions that are required to dissipate that energy. So it appears as if the effective strength is much higher than what is predicted by this other method. If we now look at the third method, which is this kinetic space method, then it doesn't pick up the matrix cracking. And the reason why it doesn't pick up the matrix cracking is because it actually computes the crack opening based not on the geometry, but based on the amount of energy dissipated. And because there is so very little energy dissipated at the beginning, then it has no way of knowing that there's been a big crack in terms of a big opening. It just simply ignores that and says, no, it's just very small, and the load is being increased up to a point where it reaches this one, and then it decreases. And as before, it actually ends up predicting a much larger crack opening, effective crack opening than the two other methods. We tried this also with another case. I will not bore you with too many cases, but this one is just to show you that we could also do a case with cracks actually cross each other. And then we had different types of mechanisms. So we pick up the lamination mechanism here, and then we pick up fiber cracking, and then matrix cracking and debonding. So that can be done as well. And you can in fact extract, in this case, two distinct traction separation laws. And as you can see the numbers here, so this is really more the lamination, which is dominated by matrix cracking, this one. So you see that this occurs actually at a relatively low stress, about 80 megapascals, 100 megapascals. And towards this one, on the other hand, this is much larger value, because this involves the fiber cracking. And again, this method here, this kinematic space method, overpredicts the strength quite significantly, just to match the energy dissipated. Whereas the approximate method here underpredicts the energy dissipated. So this one does predict the energy dissipated. The kinetic space method predicts the energy dissipated exactly, because that's the definition, and it gives you a quite reasonable value for the strength as well. A little bit of explanation of why this is happening and the difference between the two methods can be seen here, because we see that at the beginning, this is the undamaged material, and then you have the matrix here and you have the fiber. So at the beginning, what happens is that the matrix is the first one to fail. So there's a very large opening here, but the load is mostly being transmitted through the fibers. If, however, you want to look at the power, which is the product between the opening rate and the traction, then you have to compensate. And so if the kinematics are telling you that there is a big crack, and the problem here is that The big crack is in the matrix, but not the traction. The traction is being transmitted by the fibers, where there, the opening is not even there. It's very small. So you are multiplying two things which are not connected with each other. And that's why you get these discrepancies, which is that as you take an average, it is the wrong phase that is multiplied. So you do a quantity which has been averaged in the matrix, and it's been multiplied by a quantity which has been averaged in the fiber. And that's a bit of the risk and the problem with the averages, that they get disconnected in terms of which phase they're referring to. When the fibers crack, in this case, then that's the problem, that the kinematic space method over-predicts the traction to compensate for the fact that it had already given you an estimate, or a wrong estimate, if you want, for the crack opening. I'm also looking at the time, so I'm going to move on very briefly to the multiscale part, because so far we've looked at the requirement for the multiscale, but not looked at the multiscale itself. So multiscale.
Sergio, so we are about now 1 hour is gone.
Oh, yes.
So,
okay. I didn't time it. I said 45 minutes, but I should have known that I got. So, I'm gonna go very quickly. I'm gonna skip the last part of the presentation.
Yeah.
And I'm gonna try to wrap this up in about 5 minutes. Would that be okay?
Sure.
All right. So the last thing was this multiscale analysis. So for the multiscale analysis, as I said, you have to look at domains which are increasingly bigger. And then we started here from 25 microns up to 100 microns. There's also a mesh refinement that has to be done. And I had two types of specimens. The ones that we looked in the previous study, which were essentially the fibers coming out of the plane. And this newer analysis, where we have fibers running both in the vertical and direction, and also towards outside of the plane. And so we tried the two different methods, and we made a comparative analysis. The first one is this so-called kinematic space method. And as you can see, going from 50 to 75 to 100 microns, well, they all more or less fall within the same line. And we did in this case, three realizations for each one of those, because these were randomly oriented. Then we did the same thing for the other method, which is the kinematic space method. And in that case, as you can see here, it doesn't look too nice, but at least it's within the ballpark of what we would expect, which in this case was dominated by matrix cracking. So this was about 80 megapascals. And this is the other curve with the other method. And besides a few details, they pretty much give you the same response. So here the conclusion was that we did have a convergence for the microscopical volume element for both methods, and there were no significant differences. So in this context, everything seems to be all right. Surprisingly, when we went to the other type of specimen, the 090, and we tried the kinematic space method, we found a mess. So no convergence. 25, 50, 75. It was getting even worse. The 100, yeah, all over the place. And that was interesting because we thought, well, they're all consistent from the point of view of energy, but they don't seem to converge. And sometimes everything is in the way you interpret things, because we tried the other way to post-process the data, and we got a very nice convergence. So 25, 50, 75, all nicely aligned. And this is the same data. This is exactly the same simulations. So this is one way of post-processing the simulation. This is another way of post-processing the simulation. So what we discover is that it's extremely important to figure out how to do the post-processing, because when you look at the data and you process it, you get all this raw data. And if you process it the wrong way, you may conclude, well, there is no convergence. But if you process it this way, then you do conclude that there is convergence. So what we find out is that the kinetic space method is the preferred one. The kinematic space method doesn't work. So we throw it away, and then we say the kinetic space method is the way we should do the definition of the effective properties. This seems to work. So at least to wrap this part up, which I will not talk about the last part because of time, but to wrap this part up, I would say that the conclusions that we found from this analysis is that this kinematic space method should not be used. That was number one. The traction-based method, which was an approximation of the Hillman-Dell condition, the very first one that I indicated, it does a reasonable job if you want, if you find a parameter alpha that works, but it has the caveat that it does not provide you Hillman-Dell condition, satisfaction of the Hillman-Dell condition. And then this kinetic space method, in a way, was just giving up on the definition of what the crack opening is. But it seems to be, as a trade-off, but it seems to be in general quite good in terms of what it should do. I'm going to just very quickly go to my last slide. So I'm going to skip all this. I will not show you all this because there was no time. So we did some voids here. I just wanted to get to this. So in case you're interested in some of the, so I didn't have time to talk about the voids, but in case you're interested in any of these publications that we've done, so I have here the links. So this is for the European Journal of Mechanics A. This one is open access. It's the latest one that we had on these two averaging methods. And you could, if you have a smartphone, you could just simply open it, and then with your camera, you get the link. Open access, so no problem. The two other ones, you would need to have, at least your institution will need to have a subscription to Science Direct from Elsevier. But if you do, then you can also just click on that and download it. And with that, I would like to thank you for your attention and apologize for exceeding the time.
No, Sergio, we would have liked to continue, but you know, it was
Well,
very
you
interesting.
asked me
Yeah.
if I was going to get tired, and it's like you don't know me.
Okay, so I have a couple of Q&A thing in the Q&A box. So I'll just read out to you.
Okay.
So I have one from Aditya Rajesh, and he wants to know, can we calculate both phenomena separately and superimpose them? I think he's talking about two definitions of traction, which you have used.
Well, the work that I show is actually just, it's just one phenomenon, because in a sense it's just one simulation. It's about the scale transition, is how you go from the micro scale to the macroscopic one. In general, by default, in most multiscale methods, what you do, and often without even thinking, I did that at the beginning, is just to take a volume average. You say, well, the macro is the volume average, that's it. Don't even think about it. But what we discover here is that it is not. That one has to pay a bit more attention. So it's not a different phenomenon from a physical point of view. It's the same one. It's just how you post-process the data. So in one case, you could post-process the data by saying, my macroscopic stress must be this or that. And then what we are proposing here is just one specific way of defining the macroscopic quantities, which is not the average. But it does satisfy the Hillman-Dell condition, which is an important requirement. I don't know if that answers the question, but
Yeah, Aditya. Okay, can I put you live, sir? How to can put him
Yeah, yeah.
live? Okay. Okay, just a minute. So he's saying phenomena as in modes of cracking.
Sorry, the same phenomena as in?
Prabhat, you can find him in the list of participants and unmute him, so he can ask the question himself.
Okay, okay.
He's there.
Yeah, that will be easier. Yeah.
I hear something,
Aditya,
but
Aditya,
I'm
you
not.
can talk. Hello, Aditya.
Hello,
Yeah, you can.
am I audible? Yeah. No, my doubt was basically you had explained different modes of cracking, as in like delamination versus, let's say, transverse cracks and so on. So my doubt was actually in that aspect, as in if you have multiple forms of cracking happening at the same time, would a simple superimposition of the cracks work? As in, can you calculate each one separately and superimpose, or would there be effects between the modes?
No, so that's a very good question, because it also goes to the heart of how do you implement this, and it's a bit of a how should I put it? It's an open question in the sense that the philosophy here, or the approach here, would be to say, if I want to figure out what happens at the macro scale, and I don't want to do this on the fly, yeah, with the FE2 approach. You want to do it what people will call offline. So you do one simulation for all, a priori. Technically, you have to consider a infinite number of possibilities. And so I could load a material and I can pull it and then shear it at the same time, or I could change the loading path, all sorts of possibilities. Because those would generate distinct types of cracks. So you would have transverse cracks, you would have the lamination ones, and then you have all sorts of names for tunneling and you name it. I mean, it's distinct fracture mechanisms. And technically there would be an infinite possible number of combinations of all of those. And those cannot be superimposed. So it points to a certain limitation of this approach, which is that you have to a priori consider all possibilities, and it's an infinite number of them. And we have thought about this in terms of how do we do this, and actually also came to the conclusion that even though cohesive modeling is a very popular approach, it has already that fundamental flaw, which is this is more philosophical approach. Fracture mechanics, from my perspective, should be done in rate form and not in the form of a cohesive law. Cohesive law is assuming that it's always going to be like that, and that if along the way you change the way that you deform it, that your cohesive law is still valid, which is not the case. It's a bit like plasticity, that you could have a model for plasticity which is in rate form, and that would be the proper way of doing it, versus one in which you could think of plasticity as in total form, that you give the amount of deformation and then you can figure out how much plasticity has occurred, which is not possible because you need to know the path. So the same thing happens with the fracture. You need to know how this has evolved, and it's not independent of each other. So I'm rambling a bit here because it's an issue that has bothered me for a long time and is still bothering me. So the short answer is no, basically. I don't know if that answers your question.
Thank you. Thank you.
All right.
Hi, Prabhat.
You're muted, Prabhat.
Yeah, sorry. So I have two more questions. I think that case she has. I can find. Okay. So there were two questions, but I think the attendee has gone. Then there is another question. Okay, there are two hands. Sudeep Day. Sudeep Day. Yeah. So I'm allowing him to talk. Can't allow.
Yeah. Hello.
Yeah.
Hi.
Rajesh, yeah.
Hi. It was really nice to listen to you. I am also working in this field. My a specific question to you first is, uh, how do you know uh, the the properties of the RVE? This is number one question. And second is, when you are doing the averaging, how you do the averaging? I mean, if you are talking of the homogenization of the RVE, from which you are doing from the micro scale to the macro scale. I mean, if you think of, I mean, the mesoscale in between also, then how you are doing this averaging from lower scale to the higher scale?
And so with your first question, which is that the properties of the RVE, a priori you don't know how big your domain has to be in order to be an RVE. That's why you need to do this convergence analysis, in the sense that you take one domain and then you start to make it bigger and bigger. And every time you have a bigger domain, you compute the effective properties, and you check that at some point they don't change anymore. So it is part of the output. You don't know a priori the properties of the RVE. In fact, you don't even know if your microscopic volume is an RVE to begin with. You need to establish that. So you need to take different volume elements of increasing size, and every time you take the average to find the effective properties as post-processing of your microscale simulation. And once you notice that they don't change anymore, then those would be the effective properties. And then you would have established already the RVE. The point that we are making in this work is that when it comes to fracture, we should not be thinking about an RVE, but rather a surface where the crack has localized. If you try to make the average on the volume, it will never converge. You need to make an average on the crack surface, which then brings me to your second question, or the second part of your question, which is how do we connect the lower scale to the upper scale? You did mention mesoscale. In these computations, we don't have a mesoscale. We just have a small one and a large one. So micro and macro. And the way we do the average is that we take a micro scale volume element, load it until it breaks completely. And then we do the post-processing, where we identify the location of the crack. So we have an algorithm that goes element by element and tries to figure out, is this broken, yes or no? And then we connect all of them. And so we have a clever algorithm that connects this, and then we create branches. So we reconstruct what the crack is. And once we have identified those elements where the crack is, then we take the average on those elements. And that's how we extract the effective homogenized properties for fracture. I don't know if that answers your question.
Thank you. Thank you very much.
All right.
Okay, we have one more question. There are a couple more. Vikas. So he is interested to know what is Hill-Mandel condition in traction-based approximation. Its reading accuracy, which parameters following?
Could you repeat the question, because I don't.
What is what is Hill-Mandel condition in traction-based approximation?
It's the same one. So maybe I could go back and then specifically, let me go back and then try to find. Well, I don't want to do escape here. I'm just going to do the old-fashioned way of clicking. Let me see. Up. I will find it. Up. No. So where is that slide? Now you're seeing the presentation once again completely. And it should be here. Yes. All right. The Hill-Mandel condition for the crack is that I take the traction on this surface. Yeah. So every local traction here, and you multiply that by the crack opening rate. So this is the local crack opening rate here, and it's multiplied by the traction. So it gives you the power expended by opening that little piece of surface. And then what we do is that we integrate. So we take the total along this crack by taking this integral. So we first need to identify where the crack is, which we have an algorithm to do that. And once we identify that, and also including all little branches everywhere, so it's all over the place, we integrate that, and so this is the average of the product. It's the average between the traction on the crack surface and the crack opening rate. On the other hand, we have what you would have if we ignore all the details here, and we look at a continuum, a macroscopic continuum, where I ignore all the microscopic details. What I would see there is just simply one normal, one crack opening rate, one traction. Those are the equivalent macroscopic ones. And so they have exactly the same form, because continuum mechanics technically has no length scale. I could apply this at the small scale, microscopic, or at the macro scale, and I would have a traction times a crack opening rate. So if I compute it with the macro scale expression or the micro scale, the consistencies, and that's the Hill-Mandel condition, which I think was the question, is that those two should match. That condition is the same for all the methods. We have to make sure that that condition is satisfied. The approximate one is, so the room here that we have is that we can play with the definition of what is the effective traction. So we may not know exactly what the effective traction is, and we may not know what the effective crack opening is. This one we have as input. So this one we know. This one is what we can define. And so this so-called method that I have here, this approximate method, says I define the effective traction as a linear combination of a crack average and a volume average traction. And why is it approximate? Because if I define the traction this way, I know ahead of time that this quantity will not be equal to this one. It will be close. That's the approximation. It's close, but it's not equal.
So based on what you consider this alpha value, because alpha value can be varied, I mean, invariantly, it's very random in nature. Because most, when you were considering the, from lower scale to the higher scale, it may be random in nature. And particularly when when composite, particularly for the UD composite, it fails by the first ply failure. So once it is first ply failure, it's occurring, then it goes moving towards the progressive failure one after there. So in that case, based on what basis the alpha can be, we can consider that alpha value in that linear equation.
Yes. So the way the alpha is computed is essentially by doing a matching the two quantities. So if I do substitution, if I substitute here this effective traction by the expression that I have with the alpha, and I equate that to this quantity, I can compute this from a simulation. So this one comes from the simulation. This one is not defined yet exactly. This one is defined only up to a parameter alpha. However, because I want this to be equal to that approximately, that gives me a condition to determine what the alpha should be. So there's an optimal alpha, and that is given in this expression here that I will give you. So this expression here is what allows us to compute the alpha. And this is just a constant, by the way. So what you do is that you integrate from the initial time until the time in which it's completely cracked. You essentially integrate the difference between a surface average traction and a volume average traction. This one gives you the error that you introduce by having the alpha. And this particular alpha is the one that minimizes the difference between the energy dissipated computed in the macroscopic way and the energy dissipated computed in the microscopic way. So in this particular context, there is one way to compute the alpha, which is the formula that is indicated there on the screen.
Professor Basu has some question.
Yeah. Sergio, I have a sort of broad question. It seems your message is that you are trying to calibrate a coarse-grained cohesive zone model for the entire composite, right? From your microscale simulations, you are sort of trying to get an effective traction separation law. Now, at what length scale would this effective traction separation law be valid? For example, if you have like diffuse cracking in the composite, would it still hold? Because there should be a length scale involved in your effective traction separation law.
That is correct, and in fact, it's a separate piece of work, which is work in progress, by the way.
Yeah.
So you got the nail right, and then you just ping. True. There is a length scale issue here. I didn't talk about it because I already talked for about an hour, right? So, and I could talk a little bit more on this, but it's a very good question. And in fact, there are some limitations to this approach. To a certain extent, you need to have a certain separation of length scales for this to work to begin with. And what we have observed is that within the typical dimensions of plies, that we can actually get at least effective properties for the ply in one sense. Okay. And we will need to then look at a convergence where we have many plies, which requires us to have much more a bigger computational power, if I may put it that way, and in addition to that, to go to 3D. Okay. But there is an issue, and it's an issue in terms of it pretty much depends on the ratio between the cohesive zone length and the size of the ply. So when they start to collide, then we have a problem.
Right. Thank you.
So there I will agree with you that this is not something that I would use blindly everywhere. You really need to look at what is the cohesive zone length and what is the physical size of a ply. And if they start to collide, then this doesn't work.
Correct. Right.
Okay, I have one last question, if you allow, from
Sure.
Trisha. How expensive the computational cost is, given that one needs to prescribe cohesive elements everywhere in the domain?
Yeah,
And
that
if I look add
varies.
to that, how messy is it computationally with cohesive zones everywhere? Numerically, how messy is it?
Surprisingly, surprisingly good, I have to say. And in fact, I'll tell you, we tried a few things. I mean, because of course, cohesive elements, embedded cohesive elements everywhere is not the most clean approach. So I'm the first one to recognize that it's a quick and dirty type of way of doing things. Part of the issue is that when we try other methods, so we tried XFEM as well, but XFEM, when you have intersecting cracks, it becomes an issue. So for complex crack patterns, which is what we end up having everywhere, the embedded cohesive element approach seemed to be much robust to handle intersections of cracks. It does require us to embed cohesive elements everywhere, and it automatically creates a numerical issue, which is the artificial compliance coming from the compliance of the cohesive elements. Luckily, we did find a way to extract the information and then I showed that on some of the slides. I didn't talk about it, but there is a term in there which is connected to that, which is connected to the compliance from the cohesive elements. All in all, not the best technique, but at the same time, not the worst one. Computationally, simulations could vary from really whatever, from 1 hour to a couple of hours to a full day. Luckily, we so one of my students, Ruben Suarez Millan, he wrote a very nice script where we automated all the simulations. So he would automatically create the samples, run the simulations, do the post-processing, and create a database. And so we really automate not just the post-processing, but also the whole process of from a database to creating a sample, putting the properties, creating the mesh, putting the cohesive elements, running the simulation, doing the post-processing. All of that was fully automatic. So we took the person away, so we could run this every evening. It's computationally expensive, but if you have a nice script like this one, just click on that and then let it run every evening. And we didn't even notice that being a big issue. That perhaps doesn't give you the full answer, but what I want to say is that the biggest problem that we have at the moment is to go to 3D. And the first attempts did show that computational time there is a major issue. So 3D is still a bit far away. We got some results, but still far away.
Okay, let me see. Okay, so Aditya wants to ask one more question. So I'll just allow him to. So this will be probably last. So is it okay, Sergio?
Sure, sure.
Okay, okay. Aditya, you are live. You can ask directly.
Hello? Hello?
Yeah,
Am I
yeah,
audible?
yeah, yeah.
Yes. Hi again.
My doubt was the kinetic model and the kinematic model. The only difference was that we were taking one quantity as averaged and one according to the Hell-Mandel condition. No, I mean Hill-Mandel condition, and yet we have like in the kinetic one is converging very well, whereas the kinematic one is failing to converge at all. So I wanted to know what the physical reason for that was. Why one variable is making that difference, basically.
Yeah, there is in a sense no physical reason, because that does not affect the simulation. This is just the post-processing part. In other words, we took exactly the same data and we post-process it in 3 different ways. And it turned out that, and then perhaps what I could try to do is to move on. I think I had that in a little slide here. have to apologize for moving in this very clumsy way. So it should be here. All right. Okay. So this is the kinematic space method, whereby we adjust the traction to satisfy the Hell-Mandel condition, whereas the crack opening is just a geometrical average. So we take how much the cohesive elements have separated. We take an integral, and then we take the average from there. The kinetic space is exactly the opposite. We take the average traction, so we take the average force, and then we adjust the crack opening to match the Hell-Mandel condition. So in both cases, we do have an exact match for the Hell-Mandel condition. What we try to do with this little diagram here is to give a little bit of ad hoc explanation as to why we get different results because we average one way or the other. And one of the big differences has to do that we have two main constituents in this case. So we have the matrix here and the fibers. And the matrix, when you look at the cracks, they tend to occupy most of the area is matrix material. And the fibers, they only have a small amount of area where they break. But the opposite is true for the force that is being transmitted through them. So even though the matrix is quite large, it actually transmits a very small force. And in fact, it breaks very early in the process at, let's say, about 80 megapascals, then it's already broken. Whereas the fibers can go to the gigapascal range. So there's a very high contrast between those two. So the matrix is going to have a huge contribution on the kinematics. Yeah, the big crack is on the matrix side, whereas the fibers have a big contribution on the force. That's where the force is being transmitted. So part of the discrepancy is that when you look at the energy then being dissipated in the process, yeah, so how much we have to, what is the amount of work that we have to put in here to break something? It's a bit like in one case we take an average, but we're not connecting it to the right phase. So the average of the kinematics is on the matrix side. So the crack opening is mostly because of the matrix, the cracks in the matrix. But that quantity, that crack opening, has no relation to the force being transmitted because the force is being transmitted by the fibers. So you're multiplying a quantity which has been heavily averaged, or so the weight of the average comes from the matrix, and you're multiplying that with a fiber. Those two are not connected. Conversely, if you look at the force, well, actually, it's not conversely, it's the same thing. If you look at the force, you're multiplying the force, and the force is mostly coming from the fibers. And you're multiplying the work then with the opening, which is heavily influenced by the matrix. So when it comes to matching the product of those two, which is the work, in fact, the work rate, if you do it in terms of rate, then you have to make a choice. So if you take the average, kinematic average, then your tractions are going to be wrong, in the sense that they need to adjust for that product. And if your crack opening is too large, then at the beginning, when the force is small, then you would need to overcompensate for that later. So that's what's trying to be indicated here in this diagram. So if you first have a large traction, then you would have, a large opening, then you will have a smaller traction. Whereas here, you would have a small opening and then you have a larger traction. Once the fibers start to break, then it's it's a bit of the opposite that is happening here. And so what we try to do with this is it's not to show you the physics per se, but it's just to show you the reason why the two ways of averaging will provide you different results. In one case, you are putting most of the emphasis on getting the force right, and the other case, you're putting emphasis on putting the kinematics right. And our conclusion is that we should mostly focus on the force as a mean to give us a reasonable result. When you do it in terms of the getting the kinematics right, then you pay a price, which is it doesn't look like it's converging. That was a long explanation for maybe something that maybe that was not your question.
No, yeah.
Yeah, thank you,
I get it.
Sergio. I think it's clear now. Okay, so I think we are done. So, and I should say thank you. And we don't have an audience, so we'll clap for you. So,
Well, thank you.
Thanks a lot for coming in. Thanks a lot for accepting our invitation.
It's been a pleasure, and I'm happy to be virtually there in a sense, and hoping to be able to see you guys back in the Netherlands.
Yeah, sure. We are all hoping that one day we will be able to travel again.
yeah.
And,
So
and,
we'll
and I
meet maybe
better,
some
I better
conference or somewhere.
go back home soon because our partial lockdown is starting at 10 p.m. tonight. So
Yeah. Okay. Thank you for your time, Sergio.
all right,
Take
pleasure
care.
to be here.
Bye.
All right,
Bye.
bye-bye.
Sir, I have to end, or you will end?